And it is my distinct honor to introduce Dr. Vivek Kumar Singh. His talk is today titled Intrusion Detection and Mitigation Tools for Power Grid. Dr. Vivek is a senior researcher for the Cybersecurity Evaluation Application Group within NREL's Energy Security and Resilience Center. He leads a commercialization project with an industry vendor, works on 5G, securely energized and resilient NREL's Clean Energy Cybersecurity Accelerator projects. He worked at INL in the Power and Energy Systems Group in 2022 to 2021. He's also involved in proposal writing and development with internal partners and other national laboratories. His research interests include cyber physical security for the smart grid, wide area monitoring, protection and control, hybrid energy storage systems, and cyber physical federation testbeds. He has received awards from US Army Research Laboratory, NASP, and ISU. He has published research papers, patents, software disclosure records, and featured in several media articles. He received awards at Resilience Week 2018-2020 and 2020 Texas Power Energy Conference, TPEC. Dr. Vivek, it's a great honor to have you for this CARS symposium. Thank you again for accepting our invite. And now the floor is on yours to share your screen. Can you see if we can able to hear you? We can't hear you. Could you speak?
Can you hear me?
Now we can hear you. Yeah.
Okay, awesome. Nice. Yeah, I think we always have some trouble with the Zoom, so we are more like, we like Teams a lot, but it's okay to go with Zoom today.
Could you full screen the slides? Okay.
Can you see now?
That's working. It's still waiting, so let's see when it's.
Can you see now? Okay.
Yes.
Okay. Nice. Thank you, Dr. Prakash, and it was a very nice introduction. So, hey everyone, this is Vivek. I'm doing virtually presentation from NREL, and I'll be happy to talk more about the work that we are doing at NREL. So, it has been a great presentation by other two speakers, and I was able to attend them, and I can understand like they were talking a lot more into the high level cybersecurity for the power grid and the tools. And I would be presenting more into the technical details of how we develop the IDS tools, what are the mitigation tools that our national lab is working on, and how we can really help in solving this problem at the global level. So currently, when we talk about the tools that we have in the power grid, we mostly focus on the attack surfaces that are happening inside the grid network. So at this point, there is a huge expansion of the attack surfaces in the DER grid network. So if you see on the right-hand side, our grid is connected with the different types of energy system resources. We have a demand response, and then there is a huge communication network that is helping us to exchange the grid information. And also we have seen a huge integration of the DER that are being integrated with the grid network. So if you look into the cybersecurity network that we have as a grid, it's very easy to perform different types of attack reconnaissance. And currently there is no any metrics that can help us to assess both the cyber and physical side of the grid. There is a need to develop a zero trust architecture that can combine multiple cybersecurity tools. And at this point, we cannot focus on trusting any single resources. So we need to implement a zero trust architecture inside the grid network. And we are also aware of the different types of attack that happened in the grid in the past. One of them was the Ukraine grid hack that happened in 2015 and 2016. So those are the different layer of motivation that we are working together to solve this problem. At NREL, we have been developing different types of tools. Currently, we have developed three different types of tool. One is called HIDES. HIDES is the hybrid intrusion detector for energy system. We also developed a tool called IV's OT, that is a intrusion detection visualizer for the grid network. And we also have worked on developing self-healing tool, and we call them as a Stuxnet. So all three tools, as you can see here, they can be integrated over the grid network. It helps to detect different types of anomalies. They are focused on the SCADA traffic. We also have developed a visualization dashboard that can help us to see both the grid information as well as the cyber information. And we can connect these tools seamlessly so that even it will not affect the current operation of the system operator. And it could be applied in a very broad domain of the power system. And in that way, we are trying to make this tool more generalized, and it could be applied in a different levels. So I'm going to use the pointer to talk more in details in my next slides. So before we go into the tool side, let's talk about the platform that we have developed. We call it NREL Cyber Range platform. So this platform has been used for doing different level of code simulations. We can orchestrate and automate different types of attack, and also automate the defense solution so that we can do the testing in the real time. We are able to support different types of communication protocols that you might have aware in the grid network. We can integrate to multiple hardware devices that we have. So we have multiple devices from the SCL Dragos. We can integrate them into our grid network, and we can do a hardware in the loop testing for them. And one of the best part is, like, we are working on developing a visualization dashboard that will help us not to see the grid information, but also the cyber information, as you can see on this platform. So the NREL Cyber Range is like well known to different experts and researchers at National Lab, and we use them for different types of projects we are currently working on, and eventually it helps to scale the technology that we are working on, and also try to go towards the commercialization of the grid of the technology that we are developing. So NREL Cyber Range is more like a very high scale, high fidelity, as well as cyber emulation platform that we can use it to perform different types of research for the grid security. Currently, when I talk about the intrusion detection and visualization tool, we are trying to develop this tool in a way that it could be applied at the grid edge devices. And then we have a grid operator who can also get benefit of these different types of tools, and it will help them to understand what are the events that are currently happening in the grid network, as well as how to mimic those kind of events and understand their behavior so that appropriate actions could be done by the grid operators. So the tool that we have developed is very hardware agnostic. It has edge level of support. It could be scalable to multiple devices. It is also compatible with different types of grid devices, and it also supports the plug and play facility with the existing grid network. So the key features of the HIDES, as we say in general, is like it can detect both IT and SCADA specific attack. It can collect the data from different types of the grid network. It could integrate both cyber as well as grid information. And eventually we should able to see the grid information on the dashboard, and that help us to provide the accurate awareness of the grid network. Then we have a second tool called IV's OT. That tool is mostly used to see the alert on the dashboard. We can develop our own customized API and put different types of rules and integrations. So all the alerts that actually get detected by the HIDES, it is kind of connected with the IV's OT, and they can see those alerts, and then we map those alerts into different types of scenarios and database that will help to grid operator to understand what kind of anomalies has happened, how to take any actions based on those anomalies detected. And these two tools can work seamlessly with any vendor specific devices. So in that way, we have developed these two tools. So eventually it can minimize the attack surface, and it can also provide different types of information to the system operator. When we go into the deeper of how the hybrid intrusion detector work, it's basically like combining multiple types of ideas that we have at the grid network. So it combines the rule-based intrusion detector that is based on signature-based ideas that includes SNOT or a JEEK ideas. So it detects attack based on the known signatures for the SCADA network. Then we have a model-based intrusion detector that applies the spatial and temporal behavior of the grid network to detect different types of attack. And then we have a machine learning-based ideas that will use to detect attack which are very stealthy, and these attacks are performed by very advanced persistent threat actors. So these attacks are very hard to be detected by the model-based as well as rule-based ideas. So eventually what we do is like we combine these three ideas into one seamless platform. And this platform could be used to do the data integration as well as also visualize these anomalies to the system operator. And then we use like different types of open source tools that help us to develop these three different types of anomaly detector into one seamless platform. So here is the detailed method that I would like to show here. So in the network-based ideas, what happened is that it sniffs the SCADA network, and then we will put a different types of whitelisting of the network packet that include the source side as well as destination side. So from the source and destination, we look into the MAC address, IP address, and the port number. Then we filter this SCADA packet based on the given a protocol. It could be DNP3, Modbus, MMS protocol. And once we filter those packets, we apply the signature-based rules. And these rules are helpful in detecting anomalies. And anytime the anomalies are detected, it will create multiple types of alert for a given attack. And if there's no attack, it will continue the network sniffing over the wide area of communication. Then we have model-based ideas. The model-based ideas will also do the similar work. It will analyze the network and it will filter the communication packet. And here we can define the specific model that we need to, that could be based on the analog and digital values. It could also be based on the sampling rate of the packet. And finally, the behavior-based rules are developed, and it is used to detect anomalies that are mostly based on the spatial and temporal behavior on the grid side. So the reason why we want to build the model-based ideas is because once we understand the grid behavior during cyber attack, we can use that understanding and build our own models that can be helpful in detecting attack that was hard to be detected by the conventional signature-based ideas. The third one is called learning-based ideas, where we apply different types of machine learning algorithms as well as AI techniques to detect not only the cyber attack, but also identify the different types of the system events like the fault or a line tripping during maintenance. So there are multiple types of events could be detected or identified using the learning-based ideas. So the learning-based ideas mostly focus on the synchrophaser-based network. It uses the PMU data over the wide area network, and then it collects the PMU features like the bus voltages or the generation bus voltage, and then use them features to train the model eventually. Once the models are trained, it could be used to detect both malicious and actual normal events. And finally, we can use those alerts to understand what kind of event has actually happened. During the offline process of training, what we do is like we generate a library of different types of database, we label them, and we did the data pre-processing to make sure we can collect the important data and filter out the data that are not necessary. And then we do the optimal feature selection by applying some technique. Finally, it used to split the data into like a training and testing data set. And in that way, we train the model offline. And this is one of the examples for a decision tree, that if you train the model and the decision tree is already generated, then you can use that decision tree to do the online testing too. So there are three different methods that we are applying together to make sure we can detect all types of attack that can happen on the grid network. One of the challenges that we have in our previous slide is that these three methods is kind of independent of each other. And there's no any software that can do this all work together at the same time. And that's why our tool really is very helpful, because this tool is like based on the open source platform, and we are trying to integrate all these tools into one seamless platform. For example, the Suricata IDS is one we use for signature IDS. Same with the JIC or the Bro IDS. And then we have another JIC IDS that can do the model-based IDS for us. And then we use the PMU from the OpenPDC software that will collect the data from the PMU sensors. It will go all over to the Elasticsearch, all three of them. But before go to the Elasticsearch, we train the model and then generate a decision tree that could be useful for learning-based IDS. And these learning-based IDS is also communicating to the Elasticsearch along with Suricata and Bro IDS. So we have an event manager that can manage all the three events that's happening from the machine learning, model-based as well as network-based IDS. And finally, the IDS could be forwarded to the Kibana dashboard, where we can visualize the alert that is coming to the dashboard. So in that way, we are connecting all three different pieces of it and making sure they can work together. And eventually, all kinds of logs could be logged here into the Kibana dashboard. And finally, we can see what kind of attack has happened. So that is something we have developed, and we call them as a heights tool. So the main stuff that we have inside the tool is the Kibana dashboard. And we also do the storage of the data set that we might need for the machine learning training. And finally, for the model and the signature-based IDS, we use Snort, JIC, and Suricata IDS. And we have our own a private cloud network. We call it Mini Mega Co-Simulation Platform that help us to collect the data all over from the network. And we can take those power system data and then develop our own tool that can work within the grid network. This tool is kind of like already developed. We have licensed this tool, and it's also available for industry vendor. So anyone who would be interested from the vendor side, we can support their need by through the SaaS platform. And we can also help them to develop more rules and do more R&D work. So it's more like we are really interested in working with industry partner and doing some level of tool development. So that's the way we wanted to go forward with this tool. Currently, we have also did some testing for this tool over the hardware-in-the-loop testbed. So we use the RTDS, as you can see here, for modeling the grid. We have modeled like IEEE 9 bus system in the RTDS, and then we use SCADA measurements to send the data from the simulator to the grid network. We use a DNP3 protocol for doing it. And then we have a PMU measurement that is also coming from the RTDS. We use the real-time automation controller from SCL called RTAC for collecting the data over the network. And our hybrid IDS is kind of sitting over the cloud. That's a mini mega cluster cloud that can take the SCADA data from the SCADA network, and also it can apply the PMU data from the MySQL database. So in that way, it can have access of both this cyber logs as well as the PMU data that could be useful for training the model. We have considered a small controller that could be useful, and then we implemented different types of attack. In the testbed, we have done a tripping attack that can trip the relays. We have done all kind of IT attack that include denial of service and map scanning, IP spoofing. And then we also did some malware injection attack over the control center. And the reason is we wanted to test our proposed tool for different types of IDS, for different types of attack, and then use this IDS to test them. So currently, when we have done the testing, if you can see the results here, when we did the testing for the IT attack, Network IDS is kind of working very well. It can detect all kinds of IT attack that includes the denial of service, IP spoofing, and map. Model-based IDS is also performing well for the OT attack that include the malware injection attack, pulse and ramp attack into the grid network. And that's where the benefit of hybrid IDS come, where it can detect all three of the attacks. And also it can also help us to identify when the line faults are happening. And that is not possible in the model-based IDS itself. So that's the benefit of hybrid IDS, that it's not only detect the IT attack, but also it helps to detect OT as well as the line faults. We actually have done the testing for the different types of data set, and also we computed the processing time for the data set, and we can see that the decision tree is kind of performing very well. So that is one of the machine learning that we can apply for doing the testing compared to the SVM and the random forest. And we also have published this work in the IEEE conferences, and we're also working with industry partners to do some level of commercialization for this work. Second tool that we have developed is called IV's OT tool, and this tool, what it does is that it helps to visualize the anomaly, also the grid information. So it can detect, once we have detected the different types of attack, from reconnaissance to the actual data integrity attack as well as DOS attack, once they are detected, we will have a dashboard. What it does is, like, it can help you to see the anomalies, like where exactly it's happening. For example, if you see on the right hand side, the blue lines, those are like the power flows that's happening inside the grid. And those dotted spheres, as you see, those are like a cyber network. So it helps to know what network is working on for a given generation site. It will help you. It also helps to locate the IP addresses and all the information. And once we have detected those anomalies, we have a dashboard over here. And this dashboard is kind of helping us to know what kind of attack has actually happened, what is the location of those attacks. And once we have this information, it's very easy for the operator to understand it. And then they can take any kind of action they had to take to mitigate those anomalies. So this tool is called IV's OT, and that we have developed. It also generates a report that could be used for doing the forensic analysis. We can also compare the nature of the attack and when exactly it happened. So I would show you from a quick, simple example over here. So when we have a denial of service attack happen, as you can see, so these are the VMs that we have used. Those are red dots that we use to start the denial of service attack inside the network. When the attack actually happened, you can see the those arrows or the lines, they actually have disappeared when the DOS attack actually has happened. And here is where our heights tool is kind of detecting that there is a denial of service attack happen inside the grid network. Now, our main challenge is that it's very hard to understand these logs for the system operator who are not very technical expert. And that's where we see the main problem is. And for that reason, we have developed our own tool called IV's OT that will help us to give a detailed inspection of the event that happened. For example, in this case, you can see from the screen that it can tell you that network denial of service attack has happened at this timestamp. And from there, the operator can go into more details of understanding the attack, like where is the attack happen, what kind of attack happened, and which site was compromised on that. So that's where this tool is very helpful in giving a detailed event visualization of the attack that happened. And these two tools, the heights and the IV's OT, they work very parallelly together, and it could be integrated into any vendor and specific devices. And we're also trying to make it more like containerized so that it could be deployed with the vendor devices without affecting the normal operation. And that shows the benefit of this tool. The third tool I would like to talk would be called Stuxnet. So in this tool, what we are trying to do is, like, we're trying to understand the attack surfaces that can happen for the synchrophasers. So we know that the PMUs and synchrophasers, they have been used widely by the load side as well as from generation side. It helps to collect the PMU data at a very high sampling rate. And then there are many EMS applications that are currently running that uses PMUs, like voltage controller, damping oscillations, as well as wide area protection that could also be done. So what we do is like we take those PMU data over the sensors. We take both the PMU data as well as the cyber information, and then we use to develop our own intrusion detector. And then once we know we have a right anomaly detected, we then apply the alert managers that will help us to manage those alerts, and then it is forwarded to the intrusion mitigation system side. And intrusion mitigation system is basically trying to automate the different type of action that has to be done to mitigate those anomalies. So it's like a closed loop application that we're trying to build in to minimize the delay in the mitigation action. And the alert manager kind of help us to know that how to manage those alerts when they are coming to the IDS. So those alert manager will kind of help the operator also to take the different types of actions and or to initiate the mitigation action that is needed for this kind of tool. So by combining these three boxes, we are trying to build like a self-healing architecture that can not only detect anomalies but also mitigate them. So the way we have developed this tool is like we have again used the Minimega cloud platform to orchestrate the virtual environment, and then we use a Linux-based phaser data concentrator that is used to not detect but collect the PMU data over the Linux system. Then we use a tool called PySark that is used to detect the PMU packet and try to process the PMU information. Then we have a PyGMQ that is for developing the alert manager, and then again, the Minimega is again used for developing the scripting of the virtual machines. We have also licensed this tool again, and it's also available for any vendor-specific solution provider to use them. And we can also work together to build any more rules as they're required. The way it works is like we are deploying the IPDC in a KVM. KVM is like your virtual environment. It's a virtual machine environment. So anytime your PMUs get compromised through the cyber attack, say one of your local PDC was get compromised, we will generate those alerts and detect those anomalies, and then from there we will spin up a new type of PDC that would be having a similar configuration that we have. So in that way, we are trying to restore our network that was compromised here. And this is working for the PMU network, but it could also be extended to the SCADA network too. And so we have like a three boxes working together: intrusion detector, alert manager, as well as mitigation system. So these three could be connected so that we can collect the anomalies and then also provide mitigation on the top side. So we also have done the testing in the hardware in the loop test bed. For example, if you see here, we have RTDS that we use to model the grid. And then we use the local PDC, the IPDC to implement the attack and also test our proposed method. So the way we have done that, like we implemented denial of service attack as well as our spoofing attack. And once these attacks happened, the local PDC was compromised. And then we started a new local PDC that was in the standby mode. And then in that way, we are able to restore our grid network. And we use a super PDC as a central PDC to collect the data over the site. So the Stuxnet tool has a three component, as you can see here, and that's the way it works. And the bottom right figure shows you how it actually worked. So when we did the spoofing attack, the voltage magnitude measurement was coming, that has dropped down to 0. But after another local PDC2 was started, we can start seeing those voltage measurement coming back to the grid. So in that way, we are able to restore our grid information. And in that way, we can detect anomalies when it happens and then mitigate them after a few time scale. And we are able to implement this Stuxnet tool within the grid network without affecting its performance. We have also done like the comparison of this tool compared to what actually exists in the market. So we look into the different types of vendor devices that is in the market, and we are trying to understand how much benefit that we can get out of this Stuxnet tool. So when we see the SCL devices, the SCL devices do have a lot of PMU network. They can be used to simulate the PMU devices as well as integrate into the power grid. They also have a nice visualization, but they're not at this stage to develop intrusion detector and mitigation system. Dragos is kind of there. They're kind of developing different types of ideas for the PMUs. And also we look into the Digital Bond. Digital Bond is another company. It's an open source company that is doing a lot of ideas part of it, but they're not developing any mitigation. And the tool that we are proposing, it has all different types of features, and it can use to detect anomalies, mitigate anomalies. We can also see them nicely, and then it can also be used to detect different types of fault there too. So in that way, we are able to do some kind of a benefit analysis, like why somebody will like to buy this tool compared to what's in the market. So those kind of answers we are trying to find out, and then it also helps us to improve our current tool and try to develop more tools that could be integrated inside the grid network. So that's all I have for this presentation, and I would be happy to take any questions. It looked like I have 15 more minutes, so yep, thank you.
Thank you, Dr. Singh, for a great presentation. Let's see if we have more questions. And can you go back to slide 14? I thought I want to show that. Yeah, this graph, this graph between the time the second PDC kicked up, it took considerable seconds, right? Did you evaluate the comparisons of these combination of methods that you talked about to see which one where the recovery period was so quick, or is it something is due to only one approach where you observe the experimental results?
Yeah, I think that's a very good question, I would say. So we are actually trying to minimize the delay that is happening between the local PDCs getting activated as well as the time it takes. So in this case, we actually did only one-time testing, and we are trying to find a way that how the alert manager can send the data quickly to the new PDC, and then it can restart it. So one of the problem that we were trying to deal was that when the local PDC that get compromised over here, the new PDC could be like spin up, but the other challenge was that we need to send the new configuration detail to the super PDC. So that takes time to make sure that the super PDC could start talking to the new PDC, and that will require some more development, and we are working around to make sure we can minimize the delay between the new PDC getting spin up and compared to when the old PDC is getting down. So we are working on that part.
I'm looking at some questions here. So you had another slide had a list of those open source tools, and and then still find a way to license it. I wonder, how do you see the interoperability of these mini mega IPDC PyShark, and I see subscription to a SaaS platform. So I wonder, how do you perceive this in communicating to vendors to adapt your technology, and when we rely on open source tools?
Yep, that's another good question. So I think the way we are working with industry vendor is that we need some sort of like funding from the government, because so the tool that we developed, we have like tested for some specific case study, but when the vendor shows up, they would like to do testing into their own devices, and that we have not done yet. So what we do is like the way it works is like we have a DOE funding, we write proposals through it, and then we try to work together. So the best way is like we actually bring their hardware devices into our grid network, into our test bed, and we start doing the testing. And we have a very good software developer team. They are working hard to make sure like all these pieces could be connected. So Minimega is something that we have been using a lot. We have been using Minimega to create like multiple VMs, communication protocol, making the whole experiment automated. And then and that's the benefit of Minimega too, because Minimega can help you to run multiple VMs at the same time. It can also help you to start the experiment. And we also try to use like a CI/CD pipeline through the GitLab so that we can run multiple experiment and the cloud together. And the main challenge comes when the hardware in the loop devices, like when the hardware devices come in, we have to connect that with the specific port and make sure we can listen the packet. So this is a very hard problem we are trying to solve. And we also have a cloud access. So the way we are thinking would be that if we do like a containerized approach where we can put all the software, all the code into like one piece, and then use that container to do the testing with the vendor devices, that would be the one way we can support it. But at the same time, there are a lot of challenges. Working as a national lab, we have so many challenges because we are not like a company. So all the employees that working on this project may not be working next year too. They might go to some other project. So that is something we also has to deal with. And it's a kind of the challenge we always has to face it. And also, like last time we attended a DHS workshop and we kind of talked about these kind of problems. So they are also aware of this kind of situation, and they are also helping us to like train the model, like getting a new, like, like marketing these tools to the vendor side so that they are aware of it and we can do more collaboration. So those are something we're always looking for right now.
UND is also eager to collaborate on opportunities with you as you go forward. But I'm going to look at one more question here. How the malicious stripping attacks are simulated? Are you manually breaching DNP3 protocol with your agent or manually creating in runtime? This is a question coming from a user, from audience.
So malicious stripping attack, we actually implement them. So we have like a DNP3 protocol that is running. So in our testbed, we can modify those a tripping command. So it's called CROB actually. It's called select and operate command. So what we do is like, generally the DNP3, they are not encrypted. So anyone who can see the packet inside Wiresock tool, they can also see when the control signal was sent. So mostly it happened like it gets selected for a given point and then they operate it. And we can implement that one easily in a Python or any other tool, and we can just replay the stripping packet. And once we do that, it will just do the malicious stripping on the relays, and that's how we implemented the tripping attack.
Great. I think I also, one last question, if you don't mind. I think this IT/OT attack categorization, I really enjoyed this detection of hybrid, using a hybrid idea as detecting the IT/OT, but looks like there's still more room. How large is this attack data set? Do you still plan to expand more CVEs and more different signatures to this to see how you can strengthen your resilience to or evaluate different types of other attacks too? I'm assuming that's still on the work in progress, right?
Yeah, I think you're right on spot. So the attack that we considered was not much. We only consider like very few types of attack like DOS and maps, scanning and IP. But there are a lot more still the attack, like somebody can get through the enterprise network and they can try to remotely access your control center. And those will become very hard for us to detect, to be honest. And we actually working on developing those kind of attack emulation in other project, where we actually like installing a malware and then getting remote access to the system. And that kind of work is we are working is because we wanted to understand the IT/OT network that we have, the enterprise network, like how somebody can get from the enterprise network and go to the OT network. And that require a lot of understanding about the access control of those devices. And in that case, signature ideas is very hard, because once you, if somebody is doing like a malware installation, then the signature ideas is very hard for them to detect it. And that's where I think the machine learning is going to play a big role in that kind of attacks. So our goal is to go into more deeper into the AI technique and try to make our ideas more like more detailed, comprehensive, robust, and also we are working on that.
Great. Thank you so much for your time, and look forward to collaborate with you and learn more as we go along. But I think in the interest of time, I think we'll send you a nice flag if you could mail us your correct address, mailing address. So to thank you as a note for contributing to this CARS symposium. Thank you again, Dr. Vivek, for your time. Appreciate it so much for joining us today.
Yep, good to see you guys, and thank you for this great panel session or the seminar. This is very good, and I hope I can talk to you later, and we can do lot more in other conferences too. So thank you for giving this opportunity. So see you. Bye.
Thank you.